On our previous lesson, we have learned properties of electrostatic field in the electric media. And now we are going to learn something about conductors, in electrostatic field. Conductors in electrostatic field. And what can we say about conductors? What is the difference? What is the difference between conductors and the electrics? The main difference is that the electrics has only bound charges. Bound charges that are charges that cannot change their place. The charges that connected with their places, and bound charges cannot change their place. And conductors contains a lot of free charges. Conductors contains a lot of free charges, and these free charges can be quite easily moved. This is the main difference. And because of presence of free charges, conductors can conduct electric current. And because of this, they are called conductors, because they may conduct electric current. Okay, so let's have a look at one conductor. It may be any conductor. And now we are going to define field, electrostatic field inside this conductor. We are going to consider question about electrostatic field inside the conductor. What can we say in this case? Let's imagine that there are some free charges inside this conductor. If free charges are present, they will produce electrostatic field. But electrostatic field will move free charges. So it means that if there are some free charges inside a conductor, they will move because of electrostatic field. And how can they move? There are two possible ways of moving of free charges. First way, if free charges move until they get surface of conductor. And the second possibility, if they move along closed trajectory. In this case, we have electric current. But as we know about electrostatic field is potential field, and it means that electrostatic field cannot produce electric current. Why? Because to produce and support electric current, it is necessary it is necessary to produce work, to produce energy, electric energy. But electrostatic field cannot do this. Cannot do this because if we want to define work, if you want to define a work of electrostatic field, we can remember that work is linear integral from initial position to final position. And for electrostatic field, it will be for electrostatic field, it will be something like this. It will be electric charge multiplied by integral from initial position to final position. Here we have electric field intensity multiplied by dr. Okay, and what if we have closed trajectory? In case of closed trajectory, initial and final position are the same for closed trajectory. So for closed trajectory, initial position is equal to final position. And it means that in this case, for closed trajectory, we have that this work is equal to integral from R1 to R1 E dr, and it can also be signed as it can also be written as Q multiplied by integral. This round means closed trajectory. E dr is equal to 0. Because electrostatic field is always potential field, and we can write that for electrostatic field, for electrostatic field we always have linear integral on closed trajectory is always equal to 0. For electrostatic field. This is the property of potential fields. And from here we have this. We can write this property in red frame. Okay, do you have any questions about this? No questions. Okay, if there are no questions, we can make the next conclusion. we can make the next conclusion. This formula in red frame means that electrostatic field cannot produce and support electric current. Cannot produce and support electric current, and it means that there will not be electric current. Will not be electric current inside electric conductor. Inside electric conductor that is in electrostatic field only. So electrostatic field is not enough. Is not enough to support electric current. Electrostatic field is not enough for electric current, and it means that there is no electric current inside closed conductor. Again, if we have if imagine that we have some charges, free charges inside electric conductors, they will produce electrostatic field, and this electrostatic field will make free charges moving, and during the in result of this moving, these free charges will be on surface of conductor. They cannot free charges cannot move along the closed trajectory inside conductor. And from here we can conclude that there are no any free charges inside an isolated conductor. So the density of free charges inside a conductor is equal to zero. And what does it mean? It means that according to the Gauss flux theorem, we can make a conclusion. I'll remind this theorem. According to this theorem, we have that integral of electric displacement vector. D is electric displacement vector or electric induction vector, and this is equal to QS. Is equal to QS, and this is equal to triple integral VS rho U dV. But if we have that density of charges is equal to zero inside the conductor, we will have that here integral function is equal to zero, and it means that we have that this integral is equal to zero inside a conductor. And it means that in conductor inside conductor, we have electric displacement vector is equal to 0. But as we know that d electric displacement vector is always equal to epsilon 0 E. And as we know, E is not equal to 0. Epsilon 0, it is not equal to 0. And from here we can make a conclusion that inside a conductor we have electric field intensity that is equal to 0. That is equal to 0. Okay, do you have any questions about this? Do you have any questions about this? No questions. No questions. No questions. So we have that inside the conductor, electric field intensity is equal to 0. And there are no free charges inside the conductor. And because all free charges will be on the surface of conductor, only on the surface, and there are no free charges inside this conductor. So okay, and what about electrostatic potential? What about electrostatic potential? As we know from electrostatics, from one of our previous lessons, that E is equal to minus del operator of electrostatic potential, and this is the same as df by dx E plus df dy dot, and plus df by dz by dz k. So this is here we have sum of derivatives, and if derivative of function is equal to 0, it means according to calculus, it means that this function is constant. This function is constant. So it means that inside a conductor and on its surface, electrostatic potential is equal to constant inside and on a surface of conductor. So electrostatic potential is constant. Electrostatic potential is constant inside and on the surface of conductor. Electrostatic potential is always constant. Always constant. So electric charge density is 0. Electrostatic field intensity is equal to 0, and electrostatic potential is constant for conductor. Okay, and what will happen? What will happen if we remove in some way some material from outside of conductor, So let's imagine that we have made an empty place inside a conductor. That we made an empty place inside a conductor. Empty place. And because there wasn't any electrostatic field, there wasn't any electric charges, nothing will happen. Nothing will happen for after making of empty place. So after making of empty place, we will still have electrostatic field in empty place inside conductor is equal to 0, and electrostatic field inside of conductor is still equal to 0. This conclusion can be made from absence of electrostatic field and charges inside a conductor. Okay, and let's have a look at electrostatic field outside of conductor. What will be with field outside of conductor? Outside of conductor, the electrostatic field can be present. I am sorry, I have some trouble with my internet connection. But we continue. It is interesting that they have disconnect on the same day at the same time. So on Wednesday at near 1 p.m. o'clock. Interesting thing, and I cannot explain this. Okay, but we will continue. So I will return formula that disappeared after disconnect. So we have written that for electrostatic field we have this integral is equal to 0. This integral is equal to 0 for electrostatic field. So for electrostatic field, for electrostatic field we have zero. And for conductor we have For conductor, we have that electric charge density is equal to zero. Inside the conductor. Inside the conductor, electrostatic field intensity is also equal to zero. And electrostatic potential inside and on surface of conductor is always constant. Okay, and now we are going to have a look at electrostatic field outside the conductor. Outside the conductor, and outside the conductor, electrostatic field can be present. But it is necessary to say that electrostatic field cannot produce electric current. So electrostatic field is not enough to produce electric current, and it means that on a surface of conductor there will not be any electric current. There will not be any direct electric current, and it means that electric field intensity vector cannot be cannot have direction like this, for example. Like this. Why? Why? Because in this case, electrostatic field will make free charges on the surface of conductor moving. Will make them moving. So it will produce electric current. That is impossible. So it means that the angle between electric field intensity vector and the surface of conductor is always the right angle. We always have right angle between electric field intensity vector and the surface of conductor. We always have the right angle. So I will draw many vectors. But for all of them, we have the right angle. For all of them. We have the right angle between vector E, vector of electric field intensity, and the surface of conductor. So here we have the right angle between vector of electrostatic field intensity outside of the conductor and its surface, and inside the conductor, electrostatic field intensity is equal to zero. And we always have this situation. So this fact can be written that near the surface of conductor we have that absolute value of vector of electrostatic field intensity is equal to modulus of normal projection of electrostatic field intensity and normal projection on surface of conductor, Okay, and let's define let's find the connection between surface density of free charges on the surface of conductor and electrostatic field intensity near this surface. Okay, let's try to find the connection. To do this, let's consider a small part of surface of conductor. Let's consider a small part of surface, and let's use Gauss-Flux theorem for electric displacement vector. And I will choose Gauss surface. I will choose closed surface as a surface of cylinder, as a surface of little cylinder. And I will draw this. I will draw this cylinder. Here we have. I will draw this cylinder in dash because this cylinder is not something real, so it is not a real material object. It is just geometrical, something geometrical. So this is just something not real, something imagined, only geometrical object. And this cylinder can be drawn with dash lines. So this whole line is a surface of conductor, and dash line is closed geometry surface. Okay, and for upper base of cylinder, we have that vector of its area. Vector of its area is some ds. This is some ds. Because the cylinder is infinitely small. And for electrostatic field, on the surface of conductor, we have that vector of electric displacement, or electric displacement vector. We have that it is equal. It is it has the same direction as ds, because here we have the right angle, and here we have the right angle. Here we have the right angle, because recently we have proved that vector of electrostatic field intensity and also vector and also displacement, electric displacement vector, is perpendicular to the surface of conductor. And from here, from this picture, we have that electric displacement vector or electric induction vector has the same direction as vector ds. As vector ds, where ds is element, or where ds is area of upper base of the cylinder, upper base of the cylinder. And from here, we can make a conclusion. We can make a conclusion that scalar product or dot product, what is the same scalar product of d and ds vectors is equal to d, absolute value of vector d, absolute value of vector ds multiplied by cosine of 0 degrees, cosine of 0 degrees, and it is equal to d ds, ds, ds. And what does it mean? It means that we can use Gauss-Flux theorem for electric displacement vector. For electric displacement vector, I will remind that this theorem can be written in this way. This is Gauss law or Gauss-Flux theorem, where Qs is free charge inside closed surface S. Free charge inside the closed surface S. Okay, and let's use this Gauss-Flux theorem for this cylinder that is drawn with a dash line. That is drawn with dash line. I will do this. I will do this for infinitely small cylinder. For infinitely small cylinder, it means that if the cylinder is infinitely small, we will not have integral. We will have only one differential. Only one differential. So for infinitely small cylinder, according to the picture, we don't have any flux for cylinders side surface. We have flux only for upper base of this cylinder. For upper base of the cylinder, and here we have d and d multiplied by ds, and this is equal to infinitely small charge. Obviously, inside infinitely small cylinder, we will have infinitely small electric charge. Infinitely small electric charge. But as you can remember, here we have proved we have proved that scalar product d and ds in this case is equal. In this case, is equal to simple algebraic product of absolute values of vectors d and ds. So from here we have that d ds is equal to d us. No, sorry, it is not correct. We'll have this. We'll have this from here and from here. Okay, and what does it mean? What does it mean? It means that we have d absolute value of electric displacement vector or electric induction vector. What is the same? It is equal to d us divided by ds. Divided by ds. By ds. And this is equal to electric charge, surface density of electric charge. Surface density of electric charge, because charge divided by area, it is surface density. Surface density is a charge, electric charge of unit, is charge of 1 square meter of surface. Charge per 1 square meter. This is surface density, and it can be written as sigma q. Sigma q. Okay, do you have any questions about this? No questions. Okay, so I will clean some things that we already don't need, and we can write that that near the surface of conductor, near the surface of conductor, and outside of it, we have that electric displacement, absolute value of electric displacement vector is equal to surface density of electric charge. Surface density of electric charge. And we can remember from electrostatics, that or from electrostatic field properties, we can remember that d is equal to epsilon 0 e. Epsilon 0 e. And for isotropic dielectrics, E is a number, epsilon is a number, and it means that we can write that D is equal to epsilon 0 E. Epsilon 0 E. And so near the surface of conductor, we have that electric field intensity is equal to so here we have E is equal to D divided by epsilon 0. So here we have sigma Q, surface density of electric charge, divided by epsilon 0, where epsilon is relative permittivity and epsilon 0 is electric constant. So it is from here and here. Oh, here. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, if there are no questions, we can frame this. Formula. We can frame this with red. So here we have red frame around our formula. So near the surface of conductor, outside of this conductor, we have such electrostatic field that is connected to the surface density of electric charge. Okay, and let's have a look at the conductor that has such form. It has such form. And for example, here we have something like keen tip or sharp tip, and here we have a hole or pit on the surface of this conductor. But maybe I will make this picture is bigger. I will make this picture bigger. Okay, what do we have in this case? According to our previous conclusions, electrostatic field is perpendicular to the surface of conductor. Is here, and here we have this situation. Oh, sorry. Here we have this situation, because electric field intensity vector is perpendicular to the surface of conductor. Is perpendicular to the surface of conductor. And it means such directions of electric field intensity vector means that this electrostatic field will remove electric charges from it, will remove electric charges from here, and will concentrate them on a tip. So it means that electric charges on surface of conductor will concentrate on some keen sharp places on its surface. So electric charges are always concentrated on a tip of conductor, and this fact leads to big intensive electrostatic field near tip, and a little or low field inside a pit, uh, and this can be used for example in systems of lightning defense. In system of lightning defense, maybe you can maybe you have seen such systems, for example, on roofs, near some poles, antennas. We have systems of lightning defense, and these such systems always have form of tip. It is necessary to concentrate electric charges on it, and it helps to attract lightning to this and to prevent damage from lightning. Okay, and let's have a look and at one more interesting property. Let's consider electric conductor. Let's consider electric conductor inside external electrostatic field. What will be in this situation? In this situation, we'll also have these properties. In this situation, but if we have external electrostatic field that is produced by some factors, so if we have such field, for example, here we have this, and this. For example, here we have right angle, and here we will have I will draw many lines to show that the situation will be the same for all of them. Situation will be the same for all these lines. These lines are perpendicular to the surface of conductor. And on surface, negative charges will be concentrated here according to the direction of electrostatic field, and positive charges will be here. Electric charges on the surface of conductor in external electrostatic field will be redistributed on its surface in this way. Electric charges will be redistributed in this way. Okay, but inside electric conductor, there will not be any electrostatic field. And this property of electric conductors is known as shielding. 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 It is property of absence of electrostatic field inside a conductor. And sometimes, but not sometimes, it is often used in techniques. For example, for secured connection, for secured internet connection. For example, maybe you have seen so-called coaxial cable. What is this? Coaxial cable. In this cable we have there is conductor. I will draw a cross section. Of coaxial cable. We have conductor inside this. That is surrounded with conductor surrounded with conductive shape. Conductor that is surrounded with conductive shape. And the conductive shape prevents external field, prevents influence of external field on our signal. So this is a coaxial cable. Okay, and here we have that. Here it is shown that electric charges on surface of conductor is redistributed, and such redistribution of electric charges on surface of conductor inside external electrostatic field is known as electric induction. So electric induction is a redistribution of electric charges on surface of conductor in external electrostatic field. Okay, do you have any questions about this? No questions. No questions. Okay, so let's have a look at isolated conductor again. Let's have a look at isolated conductor again. Let's have a look at isolated conductor again. Have a look at isolated conductor. Near its surface, electrostatic field is proportional to electric charge density, electric charge surface density, or surface density of electric charge. But this surface density is proportional to electric charge on surface. If we have only isolated conductor, we have direct proportional between them, and it means that electric field intensity is proportional to electric charge, and this means because we have we always have that electric field intensity, electrostatic field intensity is equal to minus del operator of electrostatic potential. So from here we can conclude that electrostatic potential is proportional to electric charge on a surface of isolated conductor. And this dependence can be written with simple formula, that Q is equal to some coefficient C multiplied by electrostatic potential, or it can also be written in another way. That C is equal to electric charge, free charge on surface of conductor, divided by electrostatic potential on this surface. So we have that we have such formula on surface of conductor. on surface of a conductor. Surface of a conductor. And what is C? What is C? C is a new physical value that is known as capacitance. So C is capacitance. C is capacitance. And units for capacitance is farads. Units for capacitance is farads. Farads. Units for capacitance are farads. And from word farad. Farad is a unit of capacitance, and 1 farad, according to this definition, 1 farad is equal to 1 coulomb divided by 1 volt. Coulomb is is unit for electric charge, and the volt is unit for electrostatic potential. Electrostatic potential. Electrostatic potential or voltage. Okay, do you have any questions? No questions. No questions. And what will happen? What will happen if we have an isolated conductor, and if you place some another conductor near of it, some another conductor near of isolated conductor. There will be interaction. There will be interaction between electric charges on surfaces of these conductors, and this interaction will lead to redistribution of electric charges on the surface of conductors, and this redistribution is known as electric induction. And this redistribution of electric induction will lead to change of capacitance of conductor. So if we put some conductor near another conductor, its capacitance will change. And this property is used in for example in a capacitive touch screen. In capacitive touch screen, there are a lot of sensors. There are a lot of sensors, and these sensors are conductors. Conductors with capacitance that changes when we put our finger near the touch screen. When we put finger near touch screen, capacitance of sensors near our finger changes, and it can be detected. It can be detected, and it can be used. It can be used to to move cursor on the screen or to press button on the screen. So here we this is another practical usage of conductors with capacitance that can be changed. Okay, and the last thing for today is let's try to calculate capacitance of charged ball, conductive ball. I will draw this ball here like this, and let's imagine that there is some positive free charge on surface of this ball, in surface of this ball, and according to our previous conclusions, this charge will produce electrostatic field. And the vector of electric field intensity is perpendicular to the surface of this ball in all points of it. In all points of it will be perpendicular. It will be perpendicular. It will be perpendicular. It will be perpendicular. So here we have electric field intensity vector. That is always perpendicular to the surface of conductor. Always perpendicular to the surface of conductor. Always perpendicular to the surface of conductor. And the radius of this ball is r. And let's calculate capacitance of this ball. To do this, we have to calculate electrostatic potential on its surface. Electrostatic potential on its surface. So how to do this? First of all, we need to calculate electric field intensity, and to do this, the simplest way is to use Gauss-Flux theorem. Gauss-Flux theorem for electric displacement vector. This is the simplest way. So I will use this. ds is equal to qs, and this is equal to triple integral. This is equal to triple integral on volume inside closed surface S, rho u dv. Okay, how to use Gauss-Flux theorem? The first step is to define type of symmetry of system. We have ball. Ball has center of symmetry in the center of the ball. Center of symmetry. So the next step is to choose closed surface S, which has the same symmetry. This closed surface is sphere. It is a sphere. It is sphere that has a center. That has center in the center of the ball. So it will be sphere, and I will make it dash because this S. This sphere S, it is not a real object. It is only geometrical object. And it has some radius. It has some radius. R. It has some radius R. And here we also have the right angle. We also have the right angle. We also have the right angle. We also have the right angle here. We also have the right angle. And what does it mean? What does it mean? It means that if we draw, for example, here, if we draw element of surface S, that can be signed as ds, and this element is also perpendicular to the surface, of course, and from here we can make a conclusion that ds has the same direction as E, and of course it has the same direction. It has the same direction as vector D. I will sign this vector D. And what does it mean? What does it mean? It means that scalar product of D and ds, D and ds is equal to ds cosine 0 degrees, and this will be simple, ds, D and ds, and it means that we can simplify surface integral in Gauss-Flux theorem. S. So we can rewrite this without vectors. We can rewrite this for absolute values of vectors D and ds. For vectors D and ds. And from here, what do we have? We have center of symmetry. So ball has the center of symmetry, and it means that electrostatic field that was produced by this charged ball also has the center of symmetry, and it means that D doesn't depend on differential ds, and it means that D can be written outside of the surface integral. And this simplifies problem very much, because here we have simple integral. This integral will be the area of surface S. So this will be ds, and area of sphere is 4p r to the power of 2 d. This area of sphere. So we have calculated integral in the left side of Gauss-Flux theorem. Gauss-Flux theorem. Okay, what about the right side? First of all, it is necessary to say that we can define charge Qs without calculating triple integral. Because Qs is charge inside surface S, and charge inside surface S is charge Q on surface of the ball. So here we have that Qs is equal to Q. Very simple. Very simple. So we don't need to calculate triple integral in this case. Okay, let's use Gauss-Flux theorem. So we have to use this, and from here we obtain that 4p r to the power of 2 absolute value of the electric displacement vector, and this is equal to charge Q. This is equal to charge Q. This is equal to charge Q. Okay, do you have any questions about this? No questions. No questions. Okay, so I will clean my screen. I will clean this, and from here we have that D is equal to Q divided by 4p r to the power of 2. 4p r to the power of 2. And this situation is the same for field of point charge. And of course, it is necessary to write that it is if R that is more than radius of the ball, because in another case we will have zero. electric displacement vector will be equal to 0 in another case. Okay, and what can we say about electrostatic field intensity? Electrostatic field intensity. We know that D is equal to epsilon 0 E. And from here we have that E. No, here we have for isotropic media we have that D is equal to epsilon 0 E. And from here we have that absolute value of electric field intensity is equal to D electric displacement vector, absolute value of electric displacement vector divided by epsilon 0. So it will be Q divided by 4 P epsilon 0 R to the power of 2. R to the power of 2. R to the power of 2. And of course it is if R more than big R, more than radius of the ball. Okay, do you have any questions about this? No questions. Okay, if there are no questions, what about electrostatic potential? What about electrostatic potential? For such field, we have calculated electrostatic potential on our previous lesson, on our previous lecture. Because as you can see, electrostatic field of charged ball is the same as electrostatic field of point charge. So electrostatic potential will also be the same. As electrostatic potential for point charge. So we have phi as a function of R is equal to Q divided by 4 P epsilon 0 R. Epsilon 0 R. Of course, if we have this, and in case that we need that phi is, for R is equal to R, we will obtain Q divided by 4 P epsilon 0 R. Epsilon 0 R. And of course, capacitance will be Q divided by phi. Capacitance of conductive ball will be Q divided by phi, will be 4 P epsilon 0 R. Epsilon 0 R. Okay, do you have any questions about this? No questions. Okay, so we can write that this is capacitance. Capacitance. Capacitance of conductive ball. Capacitance of conductive ball can be calculated with such formula. Calculated with such formula. Can be calculated with such formula. And it is necessary to say, if we use this formula to calculate capacitance of a ball that has radius that is equal of radius of our planet Earth, its capacitance will be equal about 700 microfarads. So it will be quite a small value. Quite a small value. And what to do with this, we will discuss on our next lecture. Okay, do you have any questions? Okay, if there are no questions, so thank you for your attention, and I hope to meet you next week.